really lucky to have Dr. Walter Kiefer uh, uh, present to us tonight about the Europa Clipper mission, exploring an ocean world. Just as a little bit of background, and then I'll introduce Dr. Kiefer. Europa Clipper is a space probe that was launched on the 14th of October last year with Jupiter's moon Europa as its destination. It'll take a little while to get there. It's going to receive two gravity assists, one from Mars and one from Earth. And then Europa Clipper will arrive at Jupiter in April 2030. Um, at that point, it'll be in an orbit around both Jupiter and Europa, and with the aim of studying the moon of Europa at quite a much better uh, position to understand what Europa is than any other previous attempt. Um, Dr. Kiefer is a member of the NASA Europa Clipper mission. He's a member of the gravity and radio science team for Europa Clipper, and Dr. Kiefer is also director of the Lunar and Planetary Institute in Houston. And we're very fortunate to have Dr. Kiefer with us. Dr. Kiefer, from this point, I'm going to turn it over to you, but I'm going to remind people if you have a question for Dr. Kiefer, please go ahead and put it in the chat, and then when we get an opportunity, I'll moderate the questions.
So, apologies for the slow start, folks, but the question is, why Europa? The reason that we are interested in going particularly to Europa is that we have had indications going back we've known it was a special place since the Voyager observations in 1979 and 1980. When Voyager 1 and Voyager 2 flew by Europa, the first close-up images we obtained of Europa were from those two missions. And one of the things we learned early on is that it is a moon covered with a lot of tectonic activity. All of those bright red lines are tectonic structures. And that's unusual. Think about if you look at the Earth's moon or the moons of many icy satellites. This is an intensely deformed world, and more importantly, it has almost no impact craters. So Europa it's an active moon, tectonically active, and it's resurfaced itself. So we knew back in 1980 it was a special place. And then when we get to it, I'll show you close-ups in a few minutes of why things are going away. But then we also got observations from the Galileo spacecraft in the late 1990s that really strongly hint at the fact that there is an ocean of liquid water beneath this icy surface. So what you're seeing here is ice, mostly water ice, but other things as well, salts and sulfides, sulfur compounds, and other things, below which there is liquid water, and below that it's mostly actually rocky. This is not really an icy moon in the way Ganymede is or Callisto is, because they are really ice all the way to the center. This is mostly a rocky object with just an outer shell of water and ice. So let me go on and talk about some of the details. We can tell it's an active world because when we look at it in detail, we can see places where these various ridges offset each other. And so some of these ridges, for example, are they're typically a few hundred meters tall. The ridges might be, think of the ridge that's going from the lower left, especially up to the upper right, that looks like a double ridge. That's a couple of kilometers wide. But you can see places where things are cut and offset. And I'm going to try. Can you see my cursor on here or no?
Yes,
I'm guess
we can see your cursor.
I will use that as a pointer then. For instance, here, here is an old, so I'm talking mostly then about this prominent structure, but then say, look here, we've got an older structure and it is cut by this younger structure. So this sense of cutting tells us the order in which things happen. And then there's, for example, this structure that cuts the bigger structure. So there's an immense sequence of activity that's gone on here. And you can pull pieces of it apart by looking at which parts cut things and which part gets cut by other pieces. That's a thing that geologists like to do. We call that cross-cutting relations. And then let's look at a larger area which we call ice rafts. That's kind of what it looks like. These are things that are, you can see, for instance, that this and this were connected and they've been slightly joggled apart. This probably was connected here, or actually more likely here. And then some of these things have been moved much more actively apart. So this is what we call a chaos region, where the surface was actively deformed and then something below it starts moving it around. And it's a really complicated structure to try and put back together. I actually don't envy the people who try and actually figure out the geologic histories. It's complicated. But there are a group of people who like doing that, just like I'm one of the people who likes looking at gravity data and telling you what's inside. So it takes all kinds of skill sets. But clearly something is moving around, and this is the only object in the solar system other than Earth that has obvious this kind of motion on the surface. Young, recent evidence on. So there are a few impact craters like here and here, but this is young because there's hardly any craters here. Now, there are places on Venus, for instance, where I will tell you that I think we see evidence of past motions at the surface, but not active motion at the present, not in any significant way. This is a lot of motion. This is about 40 kilometers across, and there are places where there might be 10 kilometers of motion between rafts that were once connected. So this is an actively deforming surface. And you can move things on the surface of a body with the interior flowing like a viscous fluid, but the Earth's mantle we would think of as rock. If you could touch it, it would be hot, but it's solid in the way that it, for example, lets seismic waves go through it. It's not a liquid, it's not molten, but it deforms slowly a few centimeters a year. This is much younger and much more deformation, and it's got to be going on over the surface of some kind of a liquid layer. Just almost certainly. We cannot fathom how you get that level of activity without having the viscosity of the fluid be so low that it's got to be molten. And then there are things that we call dilational bands. And so again, I'll point to this structure near the lower center and point you as we go up on it. And if you look at this, it kind of looks like two pieces spreading apart, where you've got a hinge joint in the lower center. And then think about these, the dark gray disappearing and the light gray meeting up. And so again, there's a spreading sense that's going on here. And then other things that have happened on top of it. So this is superimposed on top of it. That's the other geological word that's going on here, the order of events. And let me explain superposition like this. If you are a teacher at a school and you give a test in first period, and the first person puts it down on the desk, and the second and the third as they finish it. And so you could tell the sequence in which people turn it in. And then third period, you might give the same test, and again, you'll figure that out. And the order of the stuff in the stack is the first thing in, and the first it tells you the history. And so this band, you had to have the light gray stuff, and then this separated the dark gray stuff, and then this band happened on top of it. So, and maybe here, if you got closer, you could see whether this band or this band is older. There's a history here. There's a very active history here. And that's what we really want to pull apart and understand the geology and what's driving it inside, the geophysics. And then there's the structure that we call, you look at it and it looks kind of like a catcher's mitt. And in fact, we call it the mitten. It's actually got a formal name of Murius Chaos. But this is a place where, but I promise you, people do talk about it as the mitten. because colloquial names sometimes actually stick. Um, we have to have a formal name for it because there's a process for that. But the colloquial names sometimes really do kind of take over. And this is a structure. This structure here is about 100 kilometers across. So, 60 miles. Think about something that would, if you were to sit at the center of it inside, say, center of downtown, it would extend outside the Beltway, probably in every side. It's a big structure, and not just the Beltway, but Beltway A, the Sam Houston Tollway. So it's a big place. It's about I don't have it in my notes here, but I think it's hundreds of meters high. The cliffs on the edge, you can tell it's elevated because this side is catching sunlight, this side is in shadow, and I can tell that without remembering it because if I look at the craters, things where I know are craters, the sides that are illuminated, I can then correlate that, and I know that this is in sunlight, and so this is a cliff. This is in shadow. This is a cliff, and these cliffs are hundreds of meters. So this has been pushed up from below, probably by some kind of hot ice, which is buoyant. Just like hot air rises, hot water or hot ice also, things that are expanded are somewhat less dense and they want to rise. So that's one of the clues to what's going on here. And then there aren't a lot of impact craters, but there are some. The thing is, they're often pretty well banged up. And so, for example, this is the crater Silix. It is, probably 20 kilometers across. It looks kind of like a normal crater for its size. The crater Quill is a bit smaller. Well, actually, it's a bit larger because the scale bar is the same for all of them. But it's clearly been messed up. And then the bigger structures, this is Manon. The circularity here is telling us it's probably an impact structure with lots of faults in it. It does not have an obvious deep central basin. And what we think is happening here is that small craters look just like they do on structures like places like the moon because they don't feel the bottom of the ice shell. But as they get bigger, they feel the ocean at the bottom of the ice shell and they deform. They form craters differently than they would if it were a solid body. So again, the craters are telling us something's interesting is going on. And then there's really recent observations, well, now 10 years old, of what are thought to be plumes ejecting from inside of Europa. Now, we know with absolute certainty that the Enceladus around Saturn has active plume material jetting water out of the inside of it. We are less certain about this with Europa, but they took this picture looking for it, and to understand, the Hubble picture is the background, and this picture is not Hubble. The picture of the Europa is there for context, but it's an actual Galileo image that's there for context. And this bright structure that's labeled a plume, probably when they first saw it, they would have labeled it with a question mark because it's the most prominent thing by a lot here. And so it's probably not an accident that it's coming off the limb of Europa. And then you go back and look at it 2 years later in the same place in the orbit, and oh, look, again, the same structure is there. Now, this is really at the ragged edge of what you can hope to do. And it might not be coming from the edge here of the limb. It's obviously not coming from on the side we can see, or else it would be inside of the disk. But it could be coming from someplace around the backside and projecting up. So we don't know exactly where the structure is. All we can say is it's pushing things up high enough that it gets above the limb from wherever it's coming. But this, I promise, is one of the things we will be actively looking for when we get to Europa in 2030. So look for examples of this that we could photograph, and if we're really lucky, maybe sample. With the Cassini mission flying by Enceladus, they were actually able to schedule certain flyby so that they actually could dive bomb through the plumes and sample them. It's harder to arrange that at Europa because Europa is big enough that it really actively deforms the orbit. And we can't mess up the whole sequence because of that. But we'll be looking for opportunities, depending on what we see. So, and this is an artistic rendering of what it might look like. We may see, below the surface, there's some kind of reservoir. It's spraying up. We don't know exactly what it looks like, but it's putting stuff, almost certainly putting stuff up into the shell around it, into orbit, basically. And we may get really lucky. And we've got instrumentation that will basically be looking to taste what the Europa plumes taste like, what they're composed of. And so then the last thing here about the last two slides that I want to show you about the structure of Europa before I talk about Clipper. We think that there is an ocean here. Now, so in this cutaway image, the gray, the outer part, is an ice shell of uncertain thickness. I'll come to that in a moment. And then there is a water-rich layer, liquid water, not ice, liquid water, again of an uncertain thickness, that we think is below the ice. And then below that, there's a lot of rocky material. And then below that, there will be a metal core. And so the rock and the metal are actually the same with an icy shell, are the things you would expect to see to some extent on places like Ganymede. It's the liquid ocean that makes this exciting. Although, as we look at more and more data, we think more and more bodies in the outer solar system might have oceans of some sort. But Europa is front and center, the most dynamic of them. What we don't understand is how thick this ice layer is and how thick the water layer is below that. So it could be that there's a very thin ice shell, and we've got a rocky surface here that will be creating hot magma interacting with the water and create water plumes. We see this on Earth, and probably some of the geology that we see on Europa is related to this. Or maybe there's a thick ice shell, and we've got diapirs of hot ice, but solid material that's rising because it's relatively buoyant, and other places that are falling because it's relatively less buoyant, and maybe some lenses of liquid water here. The details of the structure we do not understand at this point. That's the whole point of Europa Clipper. So let me go on, and the second half of my slides will be about Clipper as a spacecraft and a mission. This is a picture of the Clipper spacecraft being put together in one of the clean rooms at the Jet Propulsion Lab in California. It's a big spacecraft used as size indicators, all of the humans here in their clean suits. Think about having to put this whole thing together, working where basically the only part of you that's exposed is your eyes. And even there, you probably have some kind of eye goggles because you're really trying to keep this clean. Undoubtedly, there are places where it's been touched and it's been contaminated to some extent, but they tried really hard to make this, as we do with all NASA spacecraft, to make this quite clean because we don't want grease and things to cause problems, or hairs to get in instruments or whatever. So they worked really hard at that. And the size of this is, it's just the radio dish. I think that's like 4 meters across, so 12 or 13 feet. So, from bottom of the dish to top, it's at least the height of two tall people. And then as another context, this is powered by solar panels, the same kind of solar panels you might think about as having on the roof to generate electricity that are becoming more common in houses these days. But these solar panels, if you were to put this spacecraft at the center of an NBA basketball court, that court is 94 feet in length, and the solar panels, if they were fully deployed, would actually go out over the end lines of both ends of the basketball court. So this is a very big spacecraft. You need big solar panels because we're 5 times as far away, more than 5 times as far away when you get to Jupiter as we are from Earth. So the electricity you generate is only 4% of what you generate at Earth. And so if you're going to make this spacecraft work, you need a lot of power. So that's how this works. And then all of the different instruments, like this is one of the instrument rooms, and I could not possibly tell you what. But there are instruments here on one of the decks that are designed to look at the spacecraft, and it's a big, complicated thing, and it took a lot of people a number of years, right through the middle of the pandemic, to put this thing together. And then we got to launch day. I had really hoped to actually go see this launch. We had arranged a science team meeting in Florida specifically so we could all be there to see the launch. And about 4 days before we were supposed to go, and 24 hours before I was supposed to leave, I walked downstairs on Saturday mornings and said to my wife, "We're not going." And she said, "Why not?" And I said, "Hurricane Milton." Hurricane Milton suddenly sprung up out of nowhere. It became a Category 5 hurricane very quickly. And the forecast had it going right over the Kennedy Space Center. Well, it backed off in intensity, but its path stayed exactly where they were setting it was going to go. And in fact, a tornado associated with the hurricane hit the hotel where the science team was staying. Nobody was hurt. But we decided, we had just gone through, here in Houston, we had just gone through Hurricane Beryl, you'll remember last year. And I just didn't really see the idea of flying into the path of what might have been a hurricane Category 4 or 5 storm. So we stayed home, and then they said, "Oh, but the hurricane's gone. Come on out." And I said, my experience is when we have hurricanes in Houston and we're waiting for power to come back on, we don't want visitors 24 hours after the hurricane passed. Do we? I never did. So we decided we'd stay home. I know a lot of people who went. But this is the view of the spacecraft. It's a Falcon Heavy spacecraft, and usually when they do these side boosters come back and they get saved and they land at Kennedy. But they didn't do that this time. They needed because it takes fuel to bring these things back, and they needed all the fuel they could get. So they burned all of the fuel to get it going, and so they just dropped them off in the Indian Ocean somewhere. And then this is the spacecraft as it's leaving. There's the main antenna. These are the solar panels that have not yet been deployed. I think probably I'm not sure the orientation of this. I see a lot of rocket engines. This must be the bottom. And those rockets will control it getting into orbit. And we've tested them out, the small ones out at least, with maneuvers in the last year. In the introduction, you were told we're going to do a flyby of Mars. We actually did that in March. The flyby of Earth will come around Christmas time of next year, and then we are on our way to Jupiter. And this is the last time anybody will actually see any view of the spacecraft ever again. We'll just watch what it does for us. So our mission. NASA missions are always built around plans of goals and objectives. And the goal for Europa Clipper is very succinct: assess its habitability. Now, notice we have not said search for life. Search for life is tough because you don't know what the life might look like. And if you don't find life, then did you fail? But assessing habitability means, does it have the conditions for which life might exist based on what we understand about life? And that's an easier thing. I'll come back to it. And then within that, we have 3 objectives, and I'll talk about each of them in turn. Characterize the icy shell, any water below that shell, and how there is exchange between the surface of the planet, the ice, and the ocean. How do things move back and forth? Because that's a key to getting chemistry moving around that might be important for life. The second is identify the composition of any non-ice materials, anything that's not water ice. And third, characterize geological surface features. And the point is, these are achievable objectives that will get us towards understanding, is this place potentially habitable? I don't know that we will conclusively answer the question, but these are questions that we can actually physically answer. It's not useful to give a spacecraft a mission that you physically can't achieve. And we can't just say, oh, send a camera and get some great pictures. We will do that. But we actually have to have specific objectives so that we know whether the instrumentation we're planning to send is appropriate. So in terms of the geometry, the spacecraft will never go into orbit around Europa because Europa is in close to Jupiter. As the spacecraft gets close to Jupiter, it gets sped up a lot by Jupiter's gravity, and you have to lose all of that energy to go into orbit, which means you need a lot of fuel. Plus, if you get into orbit, now you're stuck in the radiation belt of Jupiter, and your spacecraft lifetime won't be very long. So what I should have put here is a dot in the center, which reflects where Jupiter is. Europa is orbiting around Jupiter every 3.5 days, and we will put Europa Clipper into an orbit that comes around every 21 days, exactly 6 times longer than Europa's there. So Europa goes around 6 times, and every 6th time we will come back and meet it at the same place. And we will then fly by over a planned 49 orbits right now. We will fly close to different parts of Europa at different times. And here the reds are the very closest places, then the yellows and the greens. And you could think of this from the perspective of Europa. You see it coming in, and it looks like a spacecraft dive bomb. It comes in, it gets very close, and then it goes back away. It never orbits Europa, but the combination of all of these spacecraft flybys lets us get a good view of most of the planet. And that's really the key to doing this, is that we get good data, but we do it in a way that's feasible from an engineering perspective. So I said our goal was to look for whether it's habitable. And so the conditions for habitability as biologists understand them for Earth right now. First is there liquid water? Well, I've told you I think that there is, but we will have data that will give us a much clearer answer about that when we're done with this mission. We know that there's ice, so we know that there's water, but if it's in solid form, it's hard to have living things there. But life likes having liquid water because it dissolves all of the relevant molecules that make life possible. Then you have to have a certain set of key elements that make all of the biologically active things. Carbon, hydrogen, oxygen, sulfur, nitrogen, phosphorus are the most important 6. And a friend of mine once told me how to remember it. He said, well, there is a lunch cake out there somewhere. He showed me a picture of one from a field trip called sponge. And so forevermore, I think of the key elements as sponge. Well, carbon's the most important, then hydrogen and oxygen. But sponge at least gets them all down. And these happen to be all elements that just have one letter for their chemical abbreviation. And then there has to be a source of energy. The energy that's making Europa active at present, that keeps it's a small body. It ought to have cooled off just like the moon is cooled off. But it goes around every 3.5 days. Io goes around every day and 3/4. Ganymede goes around once every 7 days. And so these satellites pull on each other and make the orbit slightly irregular. And so as it moves in and out by that little amount, it flexes. And I don't know if you can see my picture anymore, but I'm rubbing my hands, sliding them up and down. And if you think about doing that, this stuff slides by meters back and forth every few days. And that might not sound like much, but if you do that over the whole body for the history of the solar system, you create a lot of heat, and you can make a liquid layer. So it's the orbital behavior of Europa that drives it. But for life, that's probably not the energy source. The most likely energy source for life is going to be the chemistry. And we see life, for instance, on Earth in places like at vents coming out from the seafloor. And what drives life there is that you have a chemical equilibrium disequilibrium between the water and what's coming out. And at that place of disequilibrium where chemistry is changing over time, chemical energy can be liberated, and life is really good at taking advantage of that. So life on Earth in places like oceanic vents or deep in mines in the deep crust, take advantage of that chemical imbalance. And that's a possibility for Europa as well. I can't prove that possibility, but by characterizing the chemistry that we see, we will have a better idea whether there's energy. So we can get at all of these questions. We know now that carbon, hydrogen, oxygen, and sulfur are there. That's why I highlighted them in green. We don't know if nitrogen and phosphorus are there, and they're important. They're trace elements in comparison, but they really make a difference in the in the biochemical molecules. But all of these questions, all of these conditions are things that we can address with our spacecraft. So one more thing about habitability. Life on Earth exists in a fairly narrow range of possibilities. Most life. The pH is around 7, which is neutral. It's not either acidic or alkaline. It could be a little bit one way or the other. Temperatures around room temperature. That's the most common kind of life. But if you look at the range of life on Earth, you have things that can grow in things that are basically battery acid, and other things that are as alkaline as bleach. And they can be things that are in places that are temperatures that are cold enough to be frozen much of the time, and other places where it's hot enough that it's actually in some cases above the boiling point of water. So life on Earth exists in an incredible range of possibilities. There's some life that loves radiation, which is good if you're going to be around Europa because there's a lot of radiation from Jupiter. So I'm not suggesting that any life from Earth is there, but it tells us that there's a lot of possibilities we need to consider. And that's really the point of this slide. So I'm going to end with 3 slides that talk about how we will get to those 3 objectives. One of the objectives was the interior structure. Is there an ocean? There's an ice shelf for certain. Is there an ocean below it? How thick is the ice shelf? How thick is the ocean? And so not an accident that I put gravity first because, that's my experiment. But we will look as the spacecraft flies in and out from Jupiter or from Europa. As it gets close to Europa, it will get tugged on by the gravity of Europa. And there'll be places where there's more material and less material. And so in addition to the overall pull of the satellite, we will determine that there's more and less pull from particular places on the surface or near the surface, using what's called the Doppler effect. We will do exactly what police do to figure out if we're speeding. We will measure the velocity really, really sensitively from the radio beam. And we can analyze that in terms of how the shape of Europa changes due to tides. As it moves in and out, the surface flexes, that changes the details of the gravity. And we can basically measure the thickness of the ice shell, possible places where there are chemical variations in the shell. Are there, what is the thickness of the ocean layer maybe? Is there topography on the seafloor, on the crustal material that's deep below the ocean? We may actually be able to measure that. We'll never see that stuff directly, but we may be able to tell it's there from the gravity field. That's the hope of my team. The magnetometer will measure. Europa does not have a magnetic field of its own, but as it flies through Jupiter's magnetic field, the ocean will react to that and create what we call an induced magnetic field. And so that measurement will tell us something about the distribution of charged material in the interior, and that tells us about an ocean. And then there is a sounding radar. Certain wavelengths of radar can see right through that ice shell if they're long enough. And long enough, these are antennas that are deployed on that on those solar panels. Remember, I told you the solar panels were 100 feet across, 30 plus meters, and the radar antennas are almost as big. So we're looking to see whether radar, very very long wavelength radar, goes through the ice shell, and we're going to look for reflections, and that will tell us something about it as well. And while each of these measurements on their own are useful, together all of them will admit certain possibilities in terms of what's going on, but together they will rule out many more things. One data set may allow one set of things, and another data set will allow different things, and we may get a much tighter understanding of the interior, of Europa by the time we take all the data and put it together. We are really much better than the sum of the parts. In terms of composition, we will do things. We've got spectrometers that look at the visible and infrared and ultraviolet light to look for the fingerprints of absorptions. We do the same thing. You think about a prism separating out sunlight into its attendant things to do or stars. But we can do that with rocks, and we can measure a lot of different things about that. But beyond that, we have a mass spectrometer that if we happen to fly through gas coming out of a plume, we will directly measure what that material is made of. We can't promise that that will work. It did work on Cassini, flying through around Enceladus. Don't know if it'll work here. We may need to be a little bit lucky or get an extended mission. But that is an amazing hope, is that we can actually directly measure this. And also we can measure charged particles around Jupiter, dust around Jupiter. We've got about 5 different ways for measuring the composition of different materials coming off of Europa, and that should be really exciting. And then finally, I said geologic history. Well, I talked at the beginning about using images to interpret the history. We will get right now we have only parts of Jupiter that were studied, because if you'll remember, the Galileo mission was wonderful, but the main antenna didn't fully deploy, and so we could not send down the high resolution data we needed. We sent it down at like 20 bits a second. And so the amount of imagery we've got for Europa is we've only seen a small part of the surface at high resolution. We're going to get a global map of the whole surface at multiple wavelengths, therefore multiple colors, that we can figure out the geology and the composition, plus get high resolution views of selected features. One of the things we're going to hope for is that we may find places that we go, that will be a really exciting place to send a lander someday. Now, I don't expect to be around when we send a lander. It will be an expensive project. It may be 20 or more years in the future, but we are hoping that we can use this to point to the next step in Europa exploration. Just like Voyager pointed to Galileo and Galileo pointed to Clipper, almost certainly something will come out of Europa Clipper that will point us towards the next exploration. And then finally, thermal infrared. We will look for elevated temperatures in regions like plume eruption. And so that should be really exciting. That will be another measure. That will be perhaps the best measure of where plume sites are. Even if we can't fly through them, we will be able to map where they are being active and how they are active over time. So there's, like I said, there are about 10 instruments on this spacecraft. They all have their roles, but the combination of them is going to be really exciting, I think. And with that, I'm going to stop. I'm going to stop sharing. We can get to them. I'm going to stop sharing, and I will be happy to answer questions. I'm going to let Dawn moderate and ask the questions however you want to normally handle it, and for however long you want it to go on. I'm one of these guys, you wind me up, and you might have gotten the sense that I can talk about this mission for a long time, but at some point your people are going to want to go home and have dinner if they haven't already.
Well, that's one of the things about a remote meeting. Those that want to do, and
That's
don't
true.
worry
You're
about
actually
it.
not all in one room. But the point is, I'm willing to answer questions for a while, depending on what you guys may have queued up.
Understand. Brian Kutnick, do you want to? Would you come off of mute? You've got a couple of questions in the chat.
Yeah, I was curious how close the spacecraft is going to get to the surface of Europa on one of the closer passes.
The closest passes, I believe, are 25 kilometers from the surface.
Okay,
We don't want to get too close because you want to be a little bit careful. but I think we have a number of them down around 25 kilometers, and a lot of them are below 50 kilometers.
Okay.
Now, we will be taking data for long periods of time, about 1 to 2 hours on either side. So there'll be places where we're taking data 1,000 kilometers off the surface, but the highest resolution pictures will be taken from just above the deck, more or less. Not an awful lot higher than you are flying, only about twice as high as you're flying when you're flying in a jet airplane. You know, if you're at 35,000 feet, that's close to 12 kilometers. Within, you know, within reasonable accuracy with the math I can do in my head. And so you're only about twice as high as that. So the view will be spectacular.
And then the subsurface radar, would that be able to penetrate down to the ocean floor if there is one?
Probably not all the way down to the ocean floor. We think that the ocean is probably couple hundred kilometers deep or something. So, you know, whether we see the bottom of the ice shell with the radar depends really a lot on how thick it is, because there are circumstances where that shell might be thick enough that we don't see a reflection off the bottom of it. Just because, as you know, you have the normal problem of 1 over r squared spreading, except then it bounces and comes back up, and so it's actually 1 over r to the 4th, and so when you double the distance, you get only 1/16 of the signature back. So we may or may not see the bottom of the ice shell with the radar, depending on how thick it is. But even that will be something. If we can say, well, we could see the 20 kilometers and we didn't get a bounce, that tells us the ice shell, at least in that place, is that thick. And we'll get those measurements in a lot of places. So maybe we'll sink to the bottom in some places, not others. But we're not expecting to see the ocean floor, by which I mean the silicate rocky crust of the ocean. That's just far too deep.
That's what I was thinking of too, is the silicate crust.
But what we can hope to do is, if there's topography on that seafloor, like there is a lot on the Earth's seafloor, that creates variations in gravity, because the crustal rock is much more dense than the water. And so even though we're several hundred kilometers away from the surface, we may actually be able to see that in the gravity field. We're actively planning on that. I've got colleagues who are developing tools right now to actually be able to use this data to make inferences about what the topography on the ocean floor of Europa looks like. And the nature of that topography will tell us something interesting about the interior.
Right. Fascinating.
I just real quick comment on the back end of your answer, Dr. Kiefer. I do know for a fact that at least here on Earth, for defense purposes, it's possible to use gravitometers to detect submarines at depth in the Earth's ocean. So hopefully, you know, you'll be able to detect some structure if it's not all the way to the bottom.
Well, so okay, on Earth, we're talking about an ocean that is, and I do not believe they detect submarines that way. Notwithstanding, but what you can do that is actually important for that effect is you can map the topography of the ocean floor in exquisite detail that way. And so you see the scenes in Hunt for Red October where they're sailing through the mid-ocean ridges. That's real, although not at the speed I believe that they showed there. The problem is a submarine is so small, you won't see the gravity field at altitude. But what you will see is the details of the topography that it is hiding down in amongst. And so we definitely map the seafloor that way. That is a very common technique, and the military probably, if not, let the civilian scientists see all of it, even to this day. But what we have on the civilian side is pretty damn impressive.
Well, I can tell you for a fact, not that I was on the defense side, but I was on the oceanography, you know, offshore oil industry side. There are some really interesting tools that are out there, both with side scan sonar and gravitometers that do just exactly what you're saying, and to an extremely high resolution, the point where one of the systems I was involved with designing actually attracted Defense Department attention because
Interesting.
it
Okay.
was perhaps a little too detailed.
This is this is if we were all in person, I would probably pull you aside at the coffee break and say, "Do tell," but not going to work here. And maybe you couldn't tell.
No, I wasn't involved with anything, anything classified at that point, but
Right.
it was just really interesting. Um,
There's a lot of good stuff you can do with measuring the sea surface that way. And one of the things they actually do is they use radar from orbit, not to see to the bottom of the seafloor, but to see the deflections of the sea surface.
right.
That if they, of course, that varies with things like waves, but there are places that are going to be fixed, and that moves up and down based on the gravity below it.
Right.
And so you can measure the gravity, and therefore the gravity is telling you about the sea floor. And so it's a chain of inference. But yes, spectacular things have been being done like that since the late 1970s.
Yes.
And I'm sure I don't know the half of it because it's not a field I get followed very much.
Well, and I don't mean to take us too far off base either. So
that's fine. It's a fun conversation.
Yeah, it is. I think Will Young is on. He posted a question in the chat, but doesn't have a microphone, so I'm going to ask it for him. And his question is, how small of an object will a high resolution camera be able to image on the surface?
Oh, I'm not fully aware of the specs for the camera, but the narrow angle camera, so it has both the wide angle version of the camera and the narrow angle version of the camera, so you can get global coverage and then high resolution coverage. When we are down at the lowest altitudes, down at 25 kilometers, I'm going to guess that they are going to see down to a few meters per pixel, probably less than 10. Now, it might be off a little bit from that, but these are going to be stunning images. They are probably going to be every bit as good. The camera, the lunar reconnaissance orbiter camera that's flying around the moon now, gets down to a few meters per pixel with similar kinds of altitudes. So my guess is probably a few meters per pixel, much less than the spacing between, one line. We saw football for the first time last night, or NFL football, and the 10-yard line that you need for a first down, you would be able to image several pixels within that thing. Not enough to see individual players, but enough to get multiple pixels within that line to game.
Cool. I appreciate that. I also have a question as well regarding the radar penetration. Do you think that there's a possibility that there may be some reflections off of different thermal levels in the ocean itself? I'm thinking of, there are typically pretty major thermoclines or quite large changes in temperature over very short distances in the Earth's ocean. And I just don't know whether that would be reflective or not.
I don't know. My guess is that layers in the water are not sharp enough to create a clear reflection. But what you can hope to see, for instance, is there will be reflections off the upper surface. So one of the things this will give us is some measure of the topography. There might be layers within the ice that are really sharp reflectors. For example, if you may go from an icy layer to a brine-rich water layer, if it's wide enough, that might create a reflection. Within the water itself, due to changes in temperature or changes in salinity, my guess is those are gradational enough that they would not show it. But that structures within the ice crust we have a lot of experience, for example, and the people who are doing this, the Don Blankenship, the principal investigator for the radar, has a lot of experience using these structures, using instruments, for example, to study, to look below the surface of the Atlantic ice sheet. So
Yeah.
anything we can do on Earth, we should be able to do on at Europa. There's so much about this spacecraft that I'm not yet an expert on, and I have 4.5 years to become an expert. And we just published like 1,000 pages of descriptions of all of the instruments. I have not read all of them yet.
Okay.
But I've got 4.5 more years. But based on the physics I know, there are things we expect to see within the ice shell. I don't expect to see below the ice shell unless we're really lucky.
Okay. And one other question that I had, we know that there's at least one plume that you showed that Hubble was able to see.
Mm-hmm.
Um, will any of the orbits be targeted right at that area or approximately at that area?
I'm not sure. Well, in part, remember, we don't know exactly where that is. We
Right.
only know that it's a plume that's coming up above the limb at a particular place. And that doesn't mean maybe it's right there, or maybe it's 100 kilometers away from there, but it's jetting material up that much higher. So targeting it is difficult. And the plan for the orbits that we're going to do took years to arrange,
Gotcha.
because it's a compromise between what all of the instruments can do, and need to have happen. So if we see a plume when we get there, we'll certainly be looking for them. We probably are not going to tear apart the whole operations for the first 49 orbits, but we expect that there will be an extended mission. NASA does not tend to turn spacecraft off, at least for a while, once they've carried off the thing. And it would be a high candidate for designing the tour for an extended mission. But the first 49 orbits, I think, doing more than slight tweaks. If it happens to be that we're going to fly over it, but we need to move the orbit by 10 kilometers, yeah, that we can probably do. If we're 300 kilometers away from it, no, we can't do that, not without changing everything else after that. And we don't have the time or money to do that again.
Gotcha.
But for an extended mission, absolutely, we're going to go do that.
Well, I think that, from my point of view anyway, I think that the dream uh, 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 discovery would be that you actually go through one of those plumes and get a good sample. That would be awesome, I think.
I think everybody in the spacecraft team would agree with that, especially the people on the mass spectrometer team.
Sure.
But I'm looking forward to the day when on the cover of Science magazine is a picture of a plume from up close, and inside there's five articles showing you all of the details we got from 5 different instruments studying the plume and the geology of the surface below it. I think we can reasonably hope for that. Whether or not we get to fly through it right away, we'll have other opportunities first to do the remote data. But I think it's going to be a fabulous. We go into orbit on April the 10th or 11th of 2030. Prime mission goes through April of 2034. But I just don't think if we're successful at that point, I don't see NASA turning us off. I think we will keep going. Now, I may not still be involved in that at that point in my career or life, but I think there will be other people chomping at the bit to follow in the top behind us. And there are people who've been working on this for 20 years to try and get this thing going. And I say power to them. I came into this in 2021 after the spacecraft was already being built. I know people who have been doing this for decades. That's been the focus of their careers, and they finally are going to get to make this happen. And I'm just excited as all get out for them.
All right. If there's any other questions out there, just feel free to come off mute and ask Dr. Kiefer. Any takers? All right. Well, it sounds like we've gotten to that point, Dr. Kiefer, and I want to thank you very much for spending your time with us. And this is one of those awesome missions that we're really looking forward to seeing more about.
Okay, thank you for having me, and maybe someday you'll invite me back to tell you about what we've actually found.
Absolutely. I really look forward to that opportunity.